Morning, everyone. So yesterday we started looking into Chapter 1, Quantitative Chemistry. We started looking at two basic conversions. We introduced the notion of a mole. As we get to today's lesson, we're going to start seeing the mole is sort of in the middle of all your conversions. Yesterday we had to define what is a mole. Think of it as a box, just like we do a dozen. It pre-packs for you a certain number inside. Because we're dealing with number of particles, particles are really, really tiny. We'd expect inside a box here actually contains many, many atoms. We had said there that was called Avogadro's constant here. Basically, 1 mole, here's a number to memorize, 6.02 times 10 to the 23. Again, the kicker there is it doesn't actually specify the unit. It could be carbon, it could be magnesium, it could be hydrogen, it could be a compound, it could be anything there. But if you peek open inside the box here, they've already been pre-boxed for you, pre-packed for you. 1 mole is equivalent to an Avogadro number. On the other side here, depending on what actually is inside that box, every element here has a certain mass. We had made up an artificial unit, atomic mass unit here for carbon. We then did everything else molar mass relative to carbon being 12. And we called that conversion here, imagine I have a 1 mole, 1 box of chemical. We called this conversion here the molar mass. The mass for 1 mole. The units for this one here were grams per mole. And we just looked at the PT, which is the periodic table. So this map here helps us predict how many conversions it's going to take. On your worksheet, you had a little bit of practice. In some cases, when you were dealing with compounds, the molar mass is actually sort of the added up of all the bits. So let's just try out a quick question here. I want you to find for me, what is the mass? What is the mass of 3.2 times 10 to the 21 molecules of nickel 2 hydroxide tetrahydrate. Right? So in this question here, they're trying to get us to practice doing some of these conversions. What I would do is I would try to find ourselves on this mind map here. So I'm currently given a huge number of molecules. Molecules here is a counting number. That means I'm starting over here. And what they're interested in us finding here is interested in us calculating over for mass. Again, there is no one-step link that goes directly to mass. We would need to go first through moles as our first fraction, and then through mass. So let's see how this gets set up here. I know my final unit should be grams for mass. I'd like to write this out here as a symbol. That's why we had practiced that there. Nickel 2 hydroxide would be NiOH2. Make sure you're memorizing those polyatomics here. Tetra is the prefix for 4. We saw that for an ionic compound here, 4 waters inside. What I want you to picture here is for every 1 nickel, there's 2 hydroxides around. Somewhere left behind by that lattice there is embedded 4 waters worth. So especially as we try to do molar mass of this guy here, I need to add the mass of a nickel, I need to add twice the mass of a hydroxide, and I need to add the mass of 4 times the mass of water. Again, normally you just do that part just in your calculator. You don't need to show it, but just as we're learning it, I'm going to demonstrate for you what that would be. So let's just set up our work here, and then I'll finish up that math there. We're looking for question mark grams. Always start off with the number given. So 3.2 times 10 to the 21. Currently, it's given to me as molecules. I know it's going to take 2 fractions. The first fraction will just get rid of the numbers, either molecules or atoms. We're going to divide by molecules down here. Let's just go through moles, and then as a second fraction, let's go moles to grams, and that's where we need this math. Which is bigger, a mole or a molecule? Well, we know that the mole is, well, we have 1 mole of it, 1 box full. 1 box full is humongous. Inside of it is an Avogadro number 6.02 times 10 to the 23. Here's where it's going to become very important for you to make sure you have either use the EXP button. The EXP button will put this in brackets. It'll make sure your calculator understands to divide that entire number. On the other one here, as I mentioned, you don't normally show this work here on the side, but I'm just going to demonstrate for you here. Double check my numbers. I get nickel as 58.69. I'm just going to get the mass of oxygen and hydrogen first, 16 plus 1.01, which is 17.01. I have 2 of them, so 2 times 17.01 plus 4 times, we had done the molar mass of water, 18.02 yesterday. So 58.69, add 2 times 17.01, add 4 times 18.02, and this gives me a molar mass 164.79. It's best to say no units, but again, because this is molar mass, we're going to put grams per mole. So when there is a 164 by the G, there's a 1 by moles. The G is on top. So 164.79 divided by moles Even though you lay your work out like that, don't bother typing any times 1 or divide ones. I'm just going to go through numbers on top I multiply, on the bottom I divide. So take 3.2 10 to the 21, I multiply the 164.79, and I divide 6.02 E23, and we'll see what we get here. I want to know how heavy this amount of the hydrate do I have, and this gives me here calculator gives you 876, so I'm just going to round it to 88 grams. And there we go. We've been able to measure out. If I have 0.88 grams, I actually know exactly there are 3.2 times 10 to the 21 molecules inside. Right? So that's just a nice practice of our conversion here. Today I'm going to introduce to you sort of the reverse of that one there. So the third conversion that we're going to do. If a species exists as a molecule, so if a species is just a generic term for substance, if that thing exists as a molecule, we can count the number of atoms in one molecule. So I know the molecule would be larger. I picture one of those, and if the question is asking, well, how many carbon elements do I have, or how many oxygen elements do I have, I can actually just picture one of the molecules and actually count it from there. So let's just do a worked out example for there. So I want you to find for me how many hydrogen atoms in 2.4 moles of methane. How many hydrogen atoms are there in 2.4 moles of methane? So you go to the store, they're already pre-boxed for you as methane. You grab 2.4 boxes full, and I'm interested in counting how many hydrogen atoms there are. Now, methane is another common name I want you to memorize, just like you memorize water as H2O. Methane here is going to be CH4, right? It's a primary component of natural gas here. So what I need to be careful of here is sitting inside my box, methane itself is a molecule. Right? Methane is this grouping, CH4, CH4, CH4. I just happen to have an Avogadro number of CH4s inside. Up to this point, I've only been asking you questions. Well, how many methanes do you have? Peek open inside the box. One box has an Avogadro number inside, but you notice inside, these ones here themselves are actually molecules. What I'm interested in is just the hydrogen parts of the molecule. So I'm not actually chemically coming in and actually breaking or reacting the methane. All I'm doing is I'm saying, all right, you might know how many methanes there are. I want you to count just the hydrogens. Well, there's 4 there, there's 4 there, there's 4 there. I'm just asking you to count the number of hydrogens inside the methanes that we have. So in this case here, we do want to do this conversion here. We want to go moles to number of particles. But the only problem here is currently my moles is talking about methane. In this case here, we also have numbers of methane. Methane itself is a molecule. We still need one other conversion to get to atoms. I'll show you how that modifies our picture later on, but let's do it here. I'm interested in finding how many hydrogen atoms. If you're ever stuck, start with the number given. So we have currently 2.4 moles of methane. What I want to do is I want to get moles. I know I really want to say atoms on top, right? Moles to some counting number. But when I first peek open inside the box, unfortunately, they aren't all individual H atoms for me. They actually are currently, because this is a molecule, when we use Avogadro's number, it only tells me how many molecules there are. The analogy that we're going to have is imagine the box is like a parking lot. Inside the parking lot are a bunch of cars. Those are my molecules. I'm not interested in just the number of cars. I'm interested in the people that are sitting inside the car. So first thing you need to do is you need to say, well, I know one parking lot has an Avogadro number of all these cars, but I now need one extra conversion to say, now let's peek open inside the car itself, and I know per car, per CH4, there's actually 4 atoms. What I need to do, not a hard conversion, but I haven't seen this conversion before, I want to cancel out the molecules that we had, and I want to go to atoms, and I can say to you again, which is bigger. We're going to pretend we have one molecule, and let's count whichever people that they're interested in. So one car, one molecule. This time they're interested in just the H kind of people, H kind of atoms. So we're going to say 4 H atoms. Sometimes they say how many total atoms. In that case they're saying, well, I don't care if there's C's or H's. Just tell me there's 5 people in the car. You multiply by 5. In that case there, we can say 4 H atoms. After you multiply 2.4 times Avogadro's number, because this was a molecule, this only tells me, so just that part, 1.4 times 10 to the 24, I have that many molecules of methane, I have that many cars, and in each car there are 4 people. I then times by 4, and finally you have your answer, 5.8 times 10 to the 24. It's 4 times bigger just looking at the H atoms, just looking at the people inside of each car. Again, I want to remind you, chemically, I am not coming in and actually destroying the compound. I'm just counting just the individual particles sitting inside each of these cars here. Now, a question on sig figs here. This one here has 2 sig figs. Avogadro's number looks like 3 sig figs. Perfect. This number here looks like it's 1 sig fig. Should I, at this point, round to 6 times 10 to the 24? The question here is, well, where did this 4 come from? How sure are you that this is 4? Although we haven't done this chapter yet and actually drawing it, if I imagine a blob of CH4, how sure are you that there are 1, 2, 3, 4 H atoms exactly? Not 3.9, not 4.1. Hopefully you can say to me, infinitely confident, because this is a small counting number, this one is actually infinitely precise. So actually we're just limited by the precision on this one here, 2 sig figs, so we should actually keep our answer to 2 sig figs. That's what we do in case we're looking for atoms inside this molecule. I'm going to do one more conversion with you. This is going to be our 4th conversion, and then I'm going to summarize it for you on the mind map. Our 4th conversion, so far we've done 1 mole is Avogadro's number. For molar mass, you look on the periodic table. The third one here is in case you're looking for a number of atoms, you can count the number of atoms inside one molecule. For this 4th conversion, we are going to look back at volume. And we're going to call this one here actually molar volume. As the name suggests, volume here is the amount of space that's taken up. Space occupied by 1 mole. Right, that's why we've got that molar term. Molar mass was mass for 1 mole. Molar volume is the volume for 1 mole. But there is sort of 2 criteria here. The qualifications I'm going to make, space occupied by 1 mole, I'm going to specifically look at just gases. Gases are kind of nice because in the kinetic molecular theory, they have so much energy. They're basically, let's imagine my molecules here are little blobs here. Notice when I talk about molar volume, I'm not talking about the volume that the particles themselves take up. I'm talking about as these gases are traveling around, they're speeding around, colliding with the walls of the container, I want to know the volume of the balloon that they're actually filling up into. So we're only looking at gases. This would be not true for, let's say, solid. Solids are a little boring. They're incompressible. They already have things so tightly packed, it's a little bit hard to actually change the volume. In a similar fashion with liquids, you need really, really intense pressures and temperatures for that to actually happen. But gases, not so. There were already a lot of empty spaces. We call that empty space vacuum, and it will be really dramatically different based on what temperature and what pressure I am. So although molar volume can be defined just like that, the space occupied 1 mole of gas, we're going to qualify the temperature pressure that I'm at. Gases respond really drastically to how hot it is and how much pressure is actually applied on it. What we're going to do is we're going to specify a specific temperature. So space occupied by 1 mole of gas at a specific or specified, I'm going to call this a reference temperature and pressure. So because I'm going to want to make comparisons between different elements, if I put this on a data table, I want to make sure it's fair. Not one number was taken at a really hot temperature or one was taken at a really cold temperature. That would be unfair of me. What I'm going to do is I'm going to set a standard temperature. We're actually going to call this one here standard. This is my reference. A standard temperature pressure. We're going to shorthand that there, STP. Standard temperature pressure. Standard temperature is going to be defined for us at 0 degrees. We could have chosen any temperature that we wanted, but I choose standard temperature to be 0 because we want to use the absolute scale here. That can also sometimes be written 273 Kelvin. When we come back to this in a later lesson with gas laws, we will need to do that Kelvin. Second pressure here, for the longest time, this was actually the standard pressure of 1 atm, which is 1 atmosphere. That's the pressure you're under right now. There's roughly 1 atmosphere of gas above you. You don't really feel anything because 1 atmosphere is not a whole lot. In that case there, based on our sort of old convention, this is actually 101.3 kilopascals. For the longest time, we used to say 1 mole is 22.4 liters, right? So if you're doing regular Chem 11, regular Chem 12, you look at some old books, they're going to use 1 mole is 22.4. For IB and the new revised grade 11, grade 10, grade 12 curriculum here, we're going to change our standard pressure. We could have set it to be anything. Here's case in point of it. What if I redefine standard pressure? There's an increasingly common unit for pressure here that's actually 1 bar worth of pressure. And in this case here, 1 bar is actually equivalent to 100 kilopascals. So you see that it's not that different. It's just a smidgen under what an atmosphere is. But that difference is enough to make our molar volume. Our conversion is actually going to be 1 mole, I'm going to emphasize here, of any gas. It actually takes a 22.7. It's just IB doesn't like using liter, so we're going to instead use decimeter cube instead. Remember, we had derived way before. Decimeter cube here was equivalent to a liter. Again, the volume that I'm talking about is the volume that is sort of filled into this balloon, assuming that we are at 0 degrees, assuming that we're at 273 Kelvin, and assuming that the pressure, I'm going to always draw pictures of outside pressure. Pretty much the balloon is going to expand until the pressure inside is equal to the pressure outside, until the pressure is actually our standard of 1 bar. That said, if we're not at the standard temperature and pressure, it's not going to be 22.7. That's true. We'll come back later on to do an ideal gas law lesson to actually figure out what this conversion would equivalent be and where I get this 22.7 from. What's surprising about this here is the volume. Let me actually write this in words here. The volume only depends on what temperature and what pressure we are at. So what I'm saying to you here is, let's say I have a balloon. Let's fill it with oxygen. Now the oxygen molecule here is relatively tiny. I'm not talking about the volume the molecule itself takes up. I'm saying if I have 1 mole of oxygen inside, if we are guaranteed at this standard pressure, STP, you can always assume that. I know the size of this balloon is exactly 22.7. Now, what if I swap out this gas here? What if I swap it out for a much larger, much heavier gas? What if I put in 1 mole of xenon tetrafluoride? Now, that's already a really weird compound because that's actually a compound with xenon inside, but a much larger blob, right? But fortunately for us, we're not talking about the amount of space or the volume taken up by the compound itself. We're saying if you're at this temperature, if you're at this pressure, as you spread into this container, how big of a container do you actually fill up? In this case here, because we happen to be at the same temperature, the same pressure, the volume of this will likewise be 22.7 liters, right? So the overall volume doesn't actually matter what identity of the gas you are. So I'm going to make that note to you here. This is regardless of the type of gas. Right. One other note here before we just summarize some of this here. This standard temperature for us is 0 degrees for this chapter. From chapter 2 onwards for the rest of our course, standard temperature will be redefined for us as 25 degrees. 25 degrees is actually 298 Kelvin. Just careful, the standard temperature is a little bit different. Sometimes they call that standard ambient temperature or room temperature as well. Just careful, the standard temperature in chapter 1 is different from all your other chapters. So let's head back and let's have a look at our summary diagram again. Let me just rehash for you the diagram that we have so far. So far we had moles. The link here to mass was no problem, right? It was, the conversion was called molar mass. We used the periodic table. This time, instead of just going mole just straight to number, you saw us go moles to a molecule bubble, or I'm going to have a atom bubble. The conversion that we've done so far, I have been writing this part here actually as number. Right? If the thing happened to be a molecule, 1 mole was an Avogadro number of molecules. If the thing happened to be an atom, 1 mole was still an Avogadro number, but that was for atoms. So if you look back at yesterday's lesson for uranium, because uranium was an atom, when I used Avogadro's number, I went down this path. When I did the water or the one up above, when I did Avogadro's number, I only got to molecules. It's possible, like the methane question that we did, it's possible sitting inside of your box are actually these molecules, CH4. But the question is not just how many CH4s you have. The question is asking you how many H's do I have in those CH4 blobs. In that situation, when you actually use Avogadro's number, although we still ultimately want to get to atoms, you need to first take this branch down, figure out how many cars I have in the parking lot, and then figure out for every car how many blank atoms, whatever atoms that you're looking for that you need. So in that case there, I'm just going to say 1 mole is a certain number of blank atoms. you just picture having one of those molecules, one molecule, you just picture having one of those molecules and just counting exactly. We had 4 H atoms, or I have 5 total atoms, and in that case here, you'd actually need to go down this path here. So if the molecule exists as a sort of compounded together, and we're still interested in counting atoms, when I use Avogadro's number, it only gets you to molecules. Then you can look inside each of those cars. Well, there's 4 H people, or however number of atoms in the car. So we'll see a conversion for that there, and we'll do the other conversion. This one here does take us to a volume bubble, but I'm going to qualify this volume bubble. There were 2 constraints that we're going to always emphasize. First, we need to be guaranteed that there were gases. If this is solid or liquid, we can't use it. The other thing I want to be guaranteed is we have to be guaranteed at STP. You can assume that unless we're otherwise told, oh, temperature is actually different or pressure is different. Just assume we're at a regular temperature, regular pressure. And in that case there, the conversion by name was called molar volume. Numerically, it was also fairly simple. 1 mole, we're going to use the new standard pressure, so 22.7. We'll use decimeter cube. You can leave your answer in liter if you like, but just get used to seeing questions worded as decimeter cube as opposed to liters. So, just for some practice here, I want you to see if you can calculate. I want you to find for me what is the mass of 15 decimeter cube of oxygen gas at STP. And I want to know here too, what is the total number of atoms in 3.6 moles of ammonia. Right, so just practicing those 2 conversions. What I would do is I would just pause the video. I would try it out for yourself. Use this mind map. When you unpause it, you can check how you did. Let's take a look on our mind map here. The only number given currently is 15 decimeter cube. Decimeter cube is a measure of volume, so I'm starting here. What they're interested in here is the mass. They want to know the grams. So to convert over to mass, I need to first do a fraction. Let's get back to moles, and then let's go through mass. So let's go here. I want to know how many grams. I usually like putting the chemical here. So far we haven't jumped from one chemical to the other, but that's just good practice for you. How many grams of oxygen? We're starting with the number given, 15.0 decimeter cube of oxygen. First conversion, we'll get rid of volume and go to moles. So let's put decimeter cube down below. Top unit cancels bottom unit. Let's go to moles on top. And then let's cancel out moles on the bottom, and let's go to our gram unit on top. Which one's bigger, a mole or decimeter cube? The box is bigger, and the box we just learned for a gas at STP, because we're under these nice standard conditions, it doesn't matter what gas, we're talking about oxygen this time, that's going to be 22.7, so that number doesn't change. I'm going to divide 22.7. For the other one here, I need molar mass from the periodic table. My periodic table will tell me oxygen, element number 8, has a molar mass of 16. Do I just put 16 here? Hopefully you were able to see here, because oxygen, when it's elemental, it's actually diatomic. O would just be 16, but my molecule is actually 2 of these O's together. I actually want to double the 16. This one should actually be 32.00 grams per mole. Make sure you do have 2 decimal places, because our molar masses give us that precision. Numbers on top you multiply, on the bottom you divide. 15 times 32 divide 22.7 gives me here to 365 21.1. Make sure your final unit has grams, and there we go. So if I have a balloon that's 15 liters large, so it's about 4 milk jugs worth of volume, if I put it on a scale here, the scale would read 21.1 grams. The other question here practices the atom conversion for you. We're starting off with 3.6 moles of ammonia. So sometimes they don't start you on the fringes. I can start on moles, that's no problem. In this case here, I'm interested in counting the atoms. I'm interested in getting here. However, when they give you ammonia, another common name for you to memorize, ammonia is NH3. This is that car analogy again. I know I have 3.6 boxes. I know I want to count the people inside those boxes. But what's happening here is if I crack open the box, I can only say, sitting inside my box are all these blobs of NH3. Right? I'm looking inside my parking lot and I'm seeing these cars. So when you use Avogadro's number, although my ultimate goal is to get to atoms, because the thing itself is a molecule, I've only got 2 molecules so far. Then I need to picture, if I have 1 molecule of it, how many of whatever atoms are you looking at. So let's do this here. I'm interested in figuring out how many total atoms, right? N's and H's, I don't care. Starting off with the number here, 3.6 moles. I really want to use Avogadro's number. 1 mole is 6.02 10 to the 23, and yet, because these ones here are cars, unfortunately, I'm left with molecules. If inside of it were just plain old atoms, yesterday we did a lesson where we had a box, they were just plain old U atoms. When you actually use Avogadro's number, it already was atoms. But this time, because it was a molecule, I just have molecules there. I still need to cancel out molecules. This time, they're just asking for a total number of atoms. So for every car, I have 1 that's N kind, 3 that's H kind. Again, I coincidentally have 4 atoms total. I times the final answer by 4. 3.6 times Avogadro's times 4. Do a mental check for yourself. I am expecting a big number. 8.7 times 10 to the 24. Total atoms, some of those are N's and some of those are H's. So that should help you finish up your worksheet from yesterday. If you do have any questions, just let me know. Make sure you practice these ones here so you're fairly fast at these conversions. Thanks, guys.